Today, we learn how to standardize as we investigate Z-scores. That's today's episode for Totally Doable Stats. Today, we'll investigate a simple way to compare data that's similar but scaled differently. And we'll accomplish this using something called a Z-score. Sounds weird, right? Let's learn about it by looking at an example problem. For our sample problem, we've got Larry and David, and they're having an argument, as some guys would, about who's the greatest athlete of all time. Larry is an avid baseball fan, and he says it's Nolan Ryan. Gotta be. No brainer, right? Nolan Ryan, one of the best pitchers in the history of Major League Baseball. He's the career strikeouts leader. He retired in 1993 with 5,714 strikeouts. Fantastic pitcher. David, on the other hand, says, that's great. Nolan Ryan was all right for, an old white dude who was throwing a baseball back in Texas, played for the Houston Astros and then the Texas Rangers. He might have even played for the New York Mets for a while, but regardless, the best athlete of all time is clearly Michael Jordan. Why are we even having this conversation? Lifetime field goal percentage of almost 50%. Lifetime points per game, 31 points per game, is the NBA all-time record. And of course, Michael Jordan retired for the second time in 2003. He'd retired once and came back and led them to, three more championships, so pretty good ball player. Both of them are fantastic athletes in their own right, but if they want to settle their argument and try to figure out who's better overall, they're going to have a hard time, right? Because ERA and points per game don't exactly directly compare. So this is where we use something like a Z-test or a Z-score, because what that does is it'll take and standardize those measures in terms of standard deviation, and really give us a different kind of understanding of how they compare to everybody else within their own field. Now, to do that, we've got to have some extra information, right? We can't just have their own averages and how they did. We need to know how they compare against everybody else. So we've got to have a population mean and a population standard deviation to calculate this thing, to calculate the Z-score of x minus mu over sigma. And it so happens we have some of that information. And so for Nolan Ryan, his career ERA again was 3.19. The average in the year he retired in 1993 was 4.19 for pitchers, and the standard deviation is estimated to be somewhere around 0.862. For Michael Jordan, his career points per game was 30.1. The NBA average is surprisingly low, and this is actually from a couple years after he retired. I couldn't find one for the year he retired, so we're going to use this as an estimate. It was 9.7. Sigma is a little higher here, right? Standard deviation of 2.5 points per game. And so what we're going to do is we're going to take this information and compute the Z-score for each of them so we can really see how they compute. And so in order to do this well, we're going to actually write it out. So for Nolan Ryan, we've got x being 3.19 minus mu is 4.19, and we're going to divide that by 0.862, which you can tell is going to give me a negative number. And so if I bring this up, let's get that out of the way. We've got 3.19 minus 4.19 and divided by 0.862. And so his Z-score here is 1.16. And so that's what we're looking at. So if I map that out down here, down below, right here is where the mean would be, which is always, if I'm looking at Z-scores, Z equals 0. If I go over one standard deviation and then just a little bit more, this should be where we find Nolan Ryan Z-score. Z equals negative 1.16 is right about there. Now if we compare that to Michael Jordan, so his score was, let's get that out of the way, his score was 30.1 for x minus mu of 9.7. I'm going to divide that by sigma is 2.5. That's going to give me what? Let's clear that out. 30.1 minus 9.7 is 20.4 divided by 2.5. So his z-score is 8.16. Now, for better or worse here, since Nolan Ryan's ERA, the lower the better. For Michael Jordan's points per game, so the higher the better. So we actually are wanting to see a lower negative score for Nolan Ryan and a higher positive score for Michael Jordan. And turns out what we have, right, if this right here is z, and again, z equals 0 in the middle, Michael Jordan's going to be way up here somewhere in this tail, and probably up higher than I'm even drawing it, of 8.16. So what we're doing when we're making a comparison of z-scores like this is essentially we're recognizing we can take this graph of this z-score and, if I can get it, this one of this z-score, and actually do, well, if I don't accidentally lose it, and actually do a direct comparison to see how they line out. And we can see that for Michael Jordan, he is way over here farther. He is way over here farther to the right than Nolan Ryan is to the left. He's actually up at 8.17. So if we were to use this and say this is the be-all, end-all statistic, we would say Michael Jordan is clearly the best athlete of all time, just based on these kind of numbers. That's the benefit of z-scores. We can compare information from different sources in meaningful ways, and as you saw, this is possible with a few basic calculations, which means z-scores are totally doable stats.